material is called degenerated semiconductor. Extrinsic semiconductor are further classified into two types. Number one, N-type semiconductor, and number two, P-type semiconductor. N-type semiconductor are formed when an impurity atom with 5 electrons in valence band is added. P-type semiconductor are formed when an impurity atom with 3 electrons in valence band is added. So with the addition of these impurities, a pure semiconductor, which is called a intrinsic semiconductor, converts into an extrinsic semiconductor. Here there are some examples of and impurities with 5 valence electrons. One is phosphorus, and one is arsenic, and the impurities with 3 valence electrons have some examples: aluminium, gallium, boron, etc. Out of these impurities, the two impurities, boron and phosphorus, are preferred if we want to dope any intrinsic silicon. Means these impurities are preferred for silicon material. If we want to dope any silicon material, these impurities are preferred because they have higher affinity towards silicon. If we want to dope any silicon material, we will prefer either boron or phosphorus. Out of these impurities, if these two impurities are available, these will be preferred. Now we will study in detail what is an intrinsic semiconductor. Intrinsic semiconductor. Intrinsic semiconductor means pure semiconductor. We take an example of silicon. For this silicon, its atomic number equal to 14. Out of these 14, 2 electron will be in first shell, 8 electrons will be in second shell, and 4 electrons will be in third shell called valence shell. These 4 electrons are called valency electrons. In more detail, we can draw atomic structure of silicon. In this atomic structure, there will be 14 protons and some neutron, and around this nucleus there will be electrons orbiting. 2 electrons will be in first shell and 8 electrons will be in second shell, and remaining 4 electrons remaining 4 electrons will be in outermost shell called valence electron. Out of these 14 electrons, the valence electrons are in the outermost shell, means the distance between nucleus and these valence electrons is more as compared to other electron and nucleus. So the force of attraction between negative and positive charge, force of attraction is less. If this force of attraction is less, means these electrons can easily be removed from here and these electrons can be made free electron. This is how a bond will be broken and an electron will be removed from this outermost shell. Now we will see bond structure of silicon. In silicon, every atom every atom possess 4 valency electrons. 4 valency electrons. If these silicon atoms are in a material, the in the whole material, each silicon will try to become stable, and stability will be acquired if valence band is complete. Sorry, valency shell is complete. If for any atom its valency shell is complete, we can say that this atom is stable. And in the material, every silicon atom will try to acquire stability, and for this each silicon atom will share its electron, 4 valence electron, with other 4 adjacent silicon atoms, and a bond structure will form which will look like this silicon atom. It will be surrounded by many silicon atoms. Each silicon atom possesses 4 valence electrons. I am showing only these electrons because these electrons are easy to be removed, because the force of attraction between these electron and the nucleus is less as compared to other electrons. These silicon atoms are present in the material with with 4 valence electron. This silicon atom will acquire stability. This silicon atom will acquire stability when its valence shell will be complete, and for this purpose, this silicon atom will share its electron this electron with this silicon atom, and a bond will be formed between those two silicon atom. This electron is shared with this silicon atom, and this electron is shared with this silicon atom, and through this sharing, these these two electron will belong to both the silicon atoms. These two electron will belong to both the silicon atom. We can say that this electron belong to this silicon atom, or this electron belong to this silicon atom, and this silicon atom both. In this way, all the electrons will be shared with adjacent silicon atoms, and for this silicon. For this silicon, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons, means its valence shell is complete, and in this way all the electrons will try to complete their valence shell, and electrons will be shared with the adjacent silicon atoms. In this way, total uh, complete valence shell, complete bond structure will look like this. In this bond structure, we are saying that there are many electrons, but all these electrons are present in covalent bonds, are called bonded electrons, and the bond formed with the sharing of electron is called covalent bond. Now at T equal to 0 degrees Kelvin, all the electrons all the electrons will be in sharing, that is in covalent bonds. If all the electrons are in covalent bonds, there will be no free electrons, and an intrinsic semiconductor at T equal to 0 degrees Kelvin will behave as an insulator. It will behave as an insulator because there are no free electrons available for conduction. If there are no electrons, there will be no holes, obviously, because holes are generated when electron break a covalent bond. If now we increase temperature is increased, the bond structure which we have already studied, the covalent bonds are formed through sharing of electrons. Now if we increase temperature T, then with increase in temperature, for example, this electron gets sufficient energy from the surrounding in order to break a covalent bond. If this energy is sufficient to break a covalent bond, this electron will break the covalent bond, and this electron will move out from here and will be called as free electron. The deficiency of this electron is now will be called hole. This deficiency of electron will be completed when an electron comes here and um, form another covalent bond here. This electron which is removed from here called free electron, and now this free electron is able to take part in conduction, and the deficiency of this electron is called hole. Similar to this, many bonds will be broken. Many bonds will be broken, and the electrons are called free electron, and the deficiency is called hole. The same thing we can now see in energy band diagram. Earlier, there was no free electron in the material. All the electrons were present in valence band, and if we increase temperature, some of the electron will break the covalent bond and become free electron, and the deficiency of these electron will be shown with a hole, shown with a hole, and this hole will remain in valence band only. Similarly, there will be many covalent bonds that will be broken, and now we can see that there are many electrons available in conduction band, and there are many holes available in valence band for conduction. So we can now say, with increase in temperature, with increase in temperature with increase in temperature, an intrinsic semiconductor, which was called earlier an insulator, an intrinsic semiconductor, starts behaving like a conductor. At T equal to 0 degrees Kelvin, there was no free electron available for conduction, and now with increase in temperature, free electrons and holes are available for conduction. Hence, an intrinsic semiconductor starts behaving like a conductor. Hence, it is called a semiconductor, conducts, which do not conduct at T equal to 0 degrees Kelvin, and with increase in temperature, it starts conducting. Also, from the energy band diagram, in conduction band, we are seeing 4 electrons and 4 holes in valence band. There are four electrons in conduction band. These are electrons that take part in conduction, and these are these are hole that take part in conduction. These two type of charge carrier which take part in conduction, and we are seeing that the number of electrons in conduction band and the number of holes in valence band are equal. So in intrinsic semiconductor, we can say that P, which is called hole concentration, measured in number of holes per centimeter cube of material, is equal to N, which is called electron concentration measured in number of electrons per centimeter cube. Both are equal, and in general, in intrinsic semiconductor, it is written as P equal to N equal to Ni, where Ni is called intrinsic carrier concentration. Intrinsic carrier concentration means charge carrier concentration in intrinsic semiconductor. Charge carrier concentration in intrinsic semiconductor. It is called Ni. The Ni intrinsic carrier concentration is given, has value equal to around 2.5 into 10 raised to power 13, and its unit is written as atoms per centimeter cube, or simply per centimeter cube. for germanium material, and it is equal to around 1.5 into 10 raised to power 10 atoms per centimeter cube, or simply per centimeter cube for silicon material. For silicon material, Ni equal to 1.5 into 10 raised to power 10, and for germanium equal to 2.5 into 10 raised to power 13. This intrinsic carrier concentration, this intrinsic carrier concentration is temperature sensitive, and it is related with temperature as Ni square equal to A naught into T cube into e raised to power minus Eg0 divided by Kt, or uh, A naught, where A naught is called material constant. It depends on material. T is temperature in degrees Kelvin, and Eg0 is value of Eg at T equal to 0 degrees Kelvin, and K is called Boltzmann Boltzmann's constant. This Boltzmann constant This Boltzmann constant has value K equal to 1.38 into 10 raised to power minus 23 joules per degrees Kelvin, and equal to 8.6 into 10 raised to power minus 5 electron volts per degrees Kelvin. Here we are writing the energy unit in electron volts, so we will consider the value of K as 8.6 into 10 raised to power minus 5 electron volt per degrees Kelvin. Ni square was written equal to A naught into T cube into e raised to power minus Eg0 divided by Kt, and now I can write Ni equal to A naught into T raised to power 3 by 2 e raised to power minus Eg0 divided by twice Kt. From this equation, we can conclude that Ni depends on temperature, means Ni is directly proportional to T raised to power 3 by 2. Here we will take an example of a material called carbon, an atom called carbon, which has 4 valence electron, but it is not considered 4 valence electron, but it is not considered as semiconductor, means it is not a semiconductor. The reason behind this is, in carbon, atomic number atomic number is equal to 6. Out of these 6 electron, 2 electrons will be in first shell and 4 electron will be in valence shell. The atomic structure will be like this. This is nucleus. 6 protons are there in nucleus, 2 electrons are in first shell and 4 electrons are in valence shell. The force of attraction between these valence electron and this nucleus will be uh, sufficiently large that it can hold this electron at this place. Means, to remove this electron we will require more energy, which is not possible to be supplied. So we can um, say that there is large force of attraction between nucleus and this valence electron. So in case of carbon, it is not possible to remove this electron for the purpose of conduction. So we can say that for carbon material, this forbidden energy band gap Eg is very large. For carbon material, as this Ag is very large, it cannot conduct, and it is called as an insulator. Although it has four valence, extrinsic semiconductor, as we see, so extrinsic semiconductor are of two types, N type and P type. If we add in a pure semiconductor an impurity atom which consists of five valence electrons, the resulting material will be an n-type semiconductor. And if we add an impurity with three valence electron, the resulting semiconductor will be p-type semiconductor. Now we will see in detail what is an n-type semiconductor. For example, we have a silicon material with atomic number equal to 14, valence electrons equal to 4. Now in this silicon we will add a phosphorus atom. For phosphorus, its atomic number is equal to 15 and valence electrons are 5. This phosphorus atom with 5 valence electron will be added in a silicon with 4 valence electron. In silicon, earlier we have seen the bond structure in which every silicon atom shares its 4 valence electron with adjacent 4 silicon atom. Now a phosphorus atom will be added which has 5 valence electron instead of 4. So we will see exactly how the bond structure will look like. The whole in the whole bond structure, uh, somewhere the bond structure will look like this. A phosphorus atom is surrounded by silicon atoms. Phosphorus has total 5 valence electrons, and the silicon which are in surrounding have only 4 valence electron. Out of these 5 valence electrons of phosphorus, 4 electrons will be shared by adjacently placed 4 silicon atoms, and the bond structure of silicon material with phosphorus as an impurity will look like this. 4 of the valence electrons of phosphorus will be shared by adjacently placed 4 silicon atom, while one electron, this electron, will remain unshared in of phosphorus. Now if we assume that this material is placed at T equal to 0 degrees Kelvin. Earlier we have seen 0 degrees Kelvin means zero energy. No energy is applied to the material. At a T equal to 0 degrees Kelvin, this fifth electron, this electron, we will call it as fifth electron. This fifth electron will belong to this phosphorus atom. The atomic structure of phosphorus will contain 15 proton in the nucleus and surrounded by 15 electrons. Out of these 15 electrons, 4 electrons will be in valence shell, and uh, from this 5 valence electron, this is fifth electron. This fifth electron will be revolving around this nucleus, and this electron, we can say it is not free, means it cannot take part in conduction unless the force of attraction between this positively charged nucleus and this negatively charged electron is overcome. If we supply energy which is sufficient to overcome this force of attraction, then only this electron can bring into conduction. Otherwise this electron will be in will be there with phosphorus atom due to a force of attraction between positively charged nucleus and this negatively charged electron. So at t equal to 0 degrees Kelvin, we can say that all these electrons are in covalent bonds, while one electron with each phosphorus atom which can take part in conduction, but we have seen that this electron is also bonded with nucleus of phosphorus due to a force of attraction between them. The energy band diagram will be normal intrinsic semiconductor. There will be a conduction band, there will be a valence band, and there will be a forbidden band. There will be a little difference in energy band diagram of intrinsic semiconductor and n-type semiconductor because of different type of charge carriers present in the material. In phosphorus, one type of electron is called bonded electron. Number 2, one type of electron can be called free electron, and there is another type of electron which belong to belong to phosphorus atom. We can say this electron is not free. This electron also not free. This electron not free. They are not available for conduction. These two electrons are not available for conduction, but these two electrons have different energy because this electron is in covalent bonds, and these type of electrons are belong to phosphorus atom. These three different type of electrons are present in a material which is doped with phosphorus impurity, pentavalent impurity. The bonded electron has its energy lies in the range, this range, that is in valence band. Free electron has its energy lies in the range in conduction band, while this electron is not free, and also it is not in covalent bond. So we can say that this electron possesses different energy from this electron and this electron. um, Also we have seen that this electron belong to phosphorus due to a force of attraction which is very small, which is very small, and if we can overcome this force, we can uh, move this electron to conduction band. Means this electron can take part in conduction. So from this discussion we can now conclude that this fifth electron is can be made available for conduction if we can overcome this force of attraction which is very small. Means this electron lies very close to conduction band. Means this can be made to take part in conduction. Means this electron lies very close to conduction band, and the energy of this fifth electron lies very close to conduction band in the material, and an energy level is created ED when a pentavalent impurity atom is added to the material. ED represents the energy of fifth electrons present in the material. So we have seen the energy band diagram of an n-type semiconductor. In n-type semiconductor, there will be a valence band which represents the energy of bonded electron and holes. Conduction band will represents energy of free electrons, and there will be a discrete energy level called ED, called donor energy level, which represents energy of fifth electrons present in the material. The energy difference between conduction band and donor energy level is around 0.01 electron volt for germanium, and it is around 0.05 electron volt for silicon. Now we can see that at T equal to 0 degrees Kelvin there are no free electrons, hence no holes, because holes exist when hole is formed, hole is generated when electron break the covalent bond. There are no free electron, hence no holes. Therefore n-type semiconductor n-type semiconductor behaves as an insulator. We have a doubt in the mind that fifth electron can take part in conduction, but we have already shown that the is fifth the fifth electron is not free at as it is with the nucleus of phosphorus due to a force of attraction. So we can conclude that an n-type semiconductor will behave as an insulator at a T equal to 0 degrees Kelvin. Now we will increase temperature. The bond structure, which is already seen, each silicon will consist of 4 valence electron, while phosphorus will consist of 5 valence electron, and the bond structure will be like this. Bond structure will look like this. If we increase the temperature uh, of this silicon material doped with phosphorus, with increase in temperature, energy will be supplied. Energy will be supplied. If the energy is supplied, charge carriers can be moved to the conduction band. Electrons can be moved to the conduction band. There are two type of electrons at present. One bonded electron and one is fifth electron. Both are not free. Not free. We can uh, break the covalent bond and make this electron to take part in conduction. Also we can overcome a force of attraction and make this electron to move from donor energy level to conduction band. The energy required to move this electron in conduction band is only 0.01 electron volt or 0.05 electron volt, depend on material, germanium or silicon. While to move this electron from valence band to conduction band, we have to apply 0.0785 electron volt or 0 or 1.21 electron volt, this much of energy to move this electron from valence band to conduction band. As temperature increases, energy is supplied, and this fifth electron require a very little energy to overcome this force of attraction and to become free electron. This fifth electron will, with increase in temperature, will detach itself from the nucleus of phosphorus and free electron become free electron. With each phosphorus atom there will be a fifth electron, and it will uh, detach itself from phosphorus of nucleus and become free electron. This process of this electron becoming free is called donor level ionization is called donor level ionization. With increase in temperature, with increase in temperature, uh, these covalent bonds will also be broken, and with each covalent bond broken there will be a generation of hole, and the generated electron will be called free electron. And with we can say that with each covalent bond broken there will be generation of electron hole pair. But in case of this fifth electron there is no bond breaking process, just we have overcome a force of attraction and made this electron uh, free so that it can take part in conduction. All this process can be seen in energy band diagram as for n-type semiconductor. All the electrons were in valence band and some electrons were in donor energy level ED, which can be made to conduct if we supply some energy to the material. When temperature is increased, these electrons which are present in donor energy level represent a very uh, in donor energy level require a very less energy. So with increase in temperature, if sufficient energy is being supplied to these electrons, this electron will move from donor energy level to conduction band. When these electrons move from donor energy level to conduction band, these electron can be said free electron, and these electron now can take part in conduction. Also with this process there will be a bond breaking process in which each broken bond will generate an electron in conduction band and and a hole in valence band. And now we can see that there are some holes in valence band and there are some electrons in conduction band. From the energy band diagram we can say that these electrons are those electrons which can take part in conduction, and these holes are those charge carriers which can take part in conduction. So the electron concentration in conduction band is far greater than the hole concentration in valence band. Now we can say that in case of n-type semiconductor, the electron concentration means the electrons which take part in conduction is far greater than the hole concentration in valence band which take part in conduction. So now we have seen that electron concentration is higher than hole concentration in n-type semiconductor. Therefore, electrons and n-type of charge carriers electrons are called majority carriers in n-type semiconductor, and p are called minority carriers. Majority carrier and minority carrier. Now, in uh, in the formation of n-type semiconductor, we have added uh, impurity with 5 valence electrons. 5 valence electrons. This impurity is called pentavalent impurity. Pentavalent impurity or donor type impurity. This impurity is called donor type impurity because already we have seen that there are 15 protons in phosphorus atom, and with each phosphorus atom there are 5 valence electrons, out of which one electron will be donated to the material for conduction. Hence this type of impurity is called donor type impurity. The donor type impurity concentration means phosphorus concentration, means number of phosphorus atom per unit volume, is represented by Nd, donor type impurity concentration written in atoms per centimeter cube, equal to atomic density atomic density of semiconductor in which these donor impurity atoms are added into impurity ratio. The atomic density equal to equal to 4.422 into 10 raised to power 22 atoms per centimeter cube for germanium, and equal to 5 into 10 raised to power 22 atoms per centimeter cube for silicon. And impurity ratio impurity ratio is impurity ratio is equal to number of phosphorus atom added per number of silicon atoms. If we know the how much phosphorus atoms are added in a silicon atoms, we can get this impurity ratio, and by putting this impurity ratio we can get the donor impurity concentration impurity concentration.